La la la. Yeah.
I was still not understanding what, like, how they constructed such fundamental.
Ah.
I know that they use generators, but
Mm-hmm.
I don't know how they attach the relation to the
Right. Yeah. I also am not well versed in surgery and manifolds. Like I mean I know of it.
It's not even surgery. It's just normal complex. It's not. It might not be.
Right, but I think those things lead to those. I mean, those this kind of like I don't know. But anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I was going to try to say things of a relatively intelligent nature. We'll see if it happens. Yeah, I brought all my books today just in case. All right, so I will start by, so I skipped over an illustration of something, and I said I would come back to it, so I'm going to try to do that. I will probably regret this, but we'll try it anyway. Jonathan's like, just go on. So this is from page 63. He makes a remark about the Borel-Cantelli lemma. I'm going past that. The second illustration, he says, consider the function. I just thought maybe, perhaps this will be a useful illustration just to get us started today. Just the calculations involved here, maybe they'll open our mind a little bit. Consider the function f of x. Oh, did you understand my email, Emily? So what I was saying is that the formula that you wrote down is the formula that was in the, like the formula you wrote down and the formula I derived are the same formula.
I had no idea.
What I mean is it was like the norm to the minus 1 power. Here's the difference. So the norm, the minus 1, or the norm minus 1. See, it was...
So did I just copy it down wrong and thought it was norm?
Right, yes, but is it completely understandable why you did that? Because if you look at like the particular font in that answer, it really looks like it could go either way. It's like, I'm about 50-50 on how to interpret the...
I'm very confused with the norm inverse. That explains so much.
It's about 50-50 interpreting the formula. And so the great thing is what we worked out today by intuitive like arguments is the formula in that stack exchange thing. So I was happy. Sorry, I'll focus. So, who am I kidding? Is that going to happen? D plus 1 if x not equal to 0. And so what I'm trying to do today is just to wrap up our thoughts about the basic Lebesgue integral. Hopefully I'll conclude with a discussion, the start of a discussion about the Fourier transform. That's what I'm hoping. I'm probably going to skip the Fubini theorem. I think it would take us like a full day. And at the end of it, we just learn essentially that you can switch integrals. You know, there's a notion of iterated integral, which is the notion of iterated integrals is also meaningful in this measure theoretic integration. And it probably improves just whatever proofs you never saw before as well. Right? So it's something I think that would, I mean, I would hope I would cover that carefully if I was doing a course on measure theory, right? Not just an introduction like we are right here. So. Anyway, 0 otherwise. What's our goal in this discussion? I'm trying to follow along here. What's he do? He says that this will be useful in our discussion of the approximations to the identity in Chapter 3. So it will be useless to us because we're not covering that. But still, I think there's something useful to do here. We prove that f is integrable outside any ball. So he wants to claim the integral outside ball radius epsilon of f of x dx is less than or equal to some constant divided by epsilon, some positive constant. All right, so I think that's the claim. Now what's the proof of the claim, all right? So this is all built. Let me just remind you what we're using. Corollary 110. Corollary 110 is the engine driving this example. And that engine says if we have a series, k equals 1 to infinity, of ak of x, series of functions, where this is greater than or equal to 0, measurable, all right? For every k greater than or equal to 1, then what? I'll do the then down here. We can integrate the series of functions, or we can form the series of the integrals of said functions, and those are equal. In other words, we can reverse the order of summation and integration. Like so. And he says, furthermore, if the sum of the integrals is finite, then the series converges for almost every x. That's a follow-up sentence. If this finite, then the series ak of x converges for almost every x. All right. Let me go back to the claim then. So what he does then to work on this claim is he lets. So this is a common theme in like these kind of arguments. Is 2 to the power is often used as a tool to create things. And let's see how it works here. A to the k, a sub k rather, is x in Rd, such that 2 to the power k times epsilon is less than length of x is less than or equal to 2 to the k plus 1 times epsilon. So this defines. So how would you picture a sub k? What is this? What is a sub k? Why is a good letter for this? It's what? It's an annulus. That's right. Yeah. So what you're looking at, and it's a half. It's a clopin or opposed annulus, depending how you want to look at it. Right? Because it's got a fuzzy inside edge. Right? But it's got a solid filled in outside edge, right? Right? And of course this is just a heuristic picture because this is x1 and this is x2 through xd, right? So I said annulus, and I believe annulus, but we're talking about a higher dimensional annuli. Right? It could be like concentric spheres in R3 or something, hypersphere shell in higher dimensions, whatever. Anyway, AK. And define, all right, what are we going to define? G of x equal to is a sum k equals 0 to infinity of a sub kx of x, where a sub k of x is equal to, ooh, interesting, 1 over 2 to the k times epsilon to the power d plus 1, ooh, times the characteristic function a sub k of x. So this is non-zero and constant, right? It's non-zero and constant, the constant value being 2 to the k times epsilon to the d plus, well, to the minus d minus 1 power, when x is an element of this kth annulus, right? So if you could visualize this for a fixed epsilon but multiple k, you'd have something that, at least in 2 dimensions, would look sort of like an amphitheater or something, like a circular, like steps, you know.
Wait, what is chi ak?
This is the characteristic function, so the way chi e works is 1 if x is an e, and 0 if x is not an e, the characteristic function. So, all right, so he says, then we must have f of x is less than or equal to g of x. What? Why does he say that? We must have then f of x is less than or equal to g of x is his claim. What was f of x equal to? That, right? Why doesn't he just say if x equal to 0? I mean, weirdo. Sorry. If x equal to 0 would take less symbols on the page. You could have saved the publisher some money. It does look cooler, yes. Oh, otherwise looks cooler?
No, this way looks cooler.
Oh, okay. It's more symmetric, right? I mean, there, that's better. All right, anyway. Okay, so he says that that's less than or equal to g of x. Do you guys see that? I mean, that's got to be a calculation. I don't think that's immediately obvious. Can we calculate the series? Let x be an element of AK for a second, right? Then what's g of x equal to? Right? Because that's 1. And if d is greater than or equal to 1, can I just say that this is less than or equal to? This may be too greedy. Oh, I only have one term. Oh, thank you. Yeah, oh, yes. I shouldn't think of it this way. Ah, that is helpful. So I only have one term. So if x is an element of AK, then g of x is equal to 1 over 2 to the k epsilon over d plus 1, right? Because that's the only non-zero thing in the series, and it's just that. So why is that, for this x, less than or equal to, so this x has what? What's the condition? 2 to the k epsilon less than length of x less than 2 to the k plus 1 epsilon, right? So what inequality do I get for x to the, I want to compare it to d plus 1, right? Can I take the d plus 1 power of that? So we have 2 to the k epsilon d plus 1 less than right? So this is less than equal to 1 over or is that the wrong direction? So I'm using this one, right? I'm using this one, and so because of that, that should flip this to and that's equal to f of x, right? Which, by the way, is what we want. We want to show that f of x is smaller than or equal to g of x. But every x fits in an annuli. And since we did it for an arbitrary annulus, it follows that f of x is less than or equal to g of x. All right? Well, next then. He says, thus, the integral of f is less than or equal to the integral of g, right? And he says, since the set he calls script A equal to, so here we're looking at the open annulus with inner radius 1 and outer radius 2. So he says this gives a sub k by dilation of what? 2 to the k epsilon, right? If we look at 2 to the k epsilon times a, we get a sub k. That's not quite true. In fact, well, the equality there's bothering me now, but that's almost true. That's not quite true. I mean, it would be true if I did that. I wonder if that's a typo in the book, maybe. I don't know. we have, by the relative dilation invariance properties of the Lebesgue measure, that the measure of a to the a sub k is equal to 2k epsilon to the d power times the measure of script a, right? And he says by corollary 110, we see that see if we can do it. Integral of g is equal to the sum k equals 0 to infinity. Maybe I should actually write it out here. Let me put it in a step he hasn't written down. So we're integrating the series k equals 0 to infinity, right, of ak of x, but that's what? That's 1 over 2k epsilon to the d plus 1 characteristic function of a sub k of x dx, right? Corollary 110 says we can exchange the order of integration and summation if we've met certain conditions. Have we met them? What was there fine print? What was the fine print on the corollary 110? Non-negative. Did I erase it? No. Yeah, just non-negative and measurable. Well, I mean, this is a built from a countable sum of measures of characteristic functions. That's certainly a measurable function, right? Fine. So these a sub x's are definitely measurable. Fine, they're non-negative, sure. And what's the integral of the characteristic function? What was that? That's like a stage 1 thing, right? The measure of ak, right? So this is just straight up measure of ak. And so what does that give us? Well, but the measure of ak was what? It was 2k epsilon to the d, right? Times the measure of a without a k divided by 2k epsilon to the d plus 1. So what I'm doing is I'm using the dilation observation here to replace this with that, right? And so what happens? Oh, stuff cancels, right? We get that the integral of g is actually equal to the summation k equals 0 to infinity of the measure of a divided by what? Yeah, 2 to the k epsilon. All right, great. And so I don't understand why he's not. Oh, I keep wondering, like, why doesn't he just write down the formula for the measure of a? It's, it's just the pi r out squared minus pi r in squared. But this is in d dimensions, so generally the volume of a spherical or hyperspherical shell it's not just. I mean, you could figure it out from the. Did I assign you guys to calculate the volume of a sphere?
I think so, on the third test.
Yeah.
Yes.
So if you work that problem, we could straight up find the formula for the measure of A, because it would be the difference of, you know, the 1 versus the 2 sphere. But I guess we don't want to, he wants to leave that kind of, you know. So we pull out this fixed but positive constant, and then you've got what? We can pull out the epsilon, right? But then you're looking at 1 plus a half plus a fourth, right? Which is otherwise known as 2? Yeah. So we've got 2 ma over epsilon. And so in other words, the integral of f is less than or equal to c over epsilon, where c is equal to 2ma. But I like this calculation. I think it's good for us to go through this. Yeah. And he says, notice that the same dilation invariance property in fact shows that cool. Fun fact, we can prove that the integral over the exterior annulus, I suppose, of dx, hyperannulus, whatever you want to call the thing, x to the d plus 1 is equal to 1 over epsilon times the integral over the unit exterior annulus, or hyperannulus, what do you want to call the thing. That's cute. All right. Well, I don't regret it. We actually got through. Next, I would remind you what proposition, I'll just say it in words. Proposition 1.11 reminded us that the integral of Lebesgue integrable functions is linear, additive, monotonic, and satisfies the triangle inequality. These things are all good to repeat. Proposition 1.12 I wanted to try to work through with you guys. All right, so proposition 112, what's it say? It says that if f is integrable, on Rd, then for every epsilon greater than 0, well, one thing you can do is that there exists a set of finite measure called, let's say, B, such that the integral over BC, value of f is less than epsilon. And 2, what's that C? What was his notation B with a little upper C mean? You guys don't know? Is it complement? It's complement. So my votes are either for complement or for closure, but you guys are sure about complement. It's not closure, okay. You guys are right. Complement is given on page 2. So it would be the complement with respect to the universe here, which would be Rd. So, whoa. Hey, that's pretty cool. That means that if the integral of f exists, which I think here means it's finite, right? This section, I think integrable means that the Lebesgue integral. Remember, he defined the extended integral momentarily, and then he said that if that extended integral is finite, then the function is said to be integrable, Lebesgue integrable. So I believe that for f to be integrable on RD means that the integral over the whole thing, right, is less than infinity, right? And so what this is saying is that if this integral is less than infinity, you can find a ball such that everything outside that ball contributes at most epsilon for the whole, for the integration. That's actually a kind of comforting result. I mean, that actually makes a lot of sense if you think about it. If you couldn't do that, it seems like the integral should blow up, And there is a delta greater than 0 such that the integral over E of f value of f is less than epsilon whenever the measure of E is less than delta. That says if you look at integration over sets of a certain size, they can't be that big. Actually, he says this last condition is known as absolute continuity. All right, so this second one is known as absolute continuity. So another way of reading proposition 1.12 is that integrability implies absolute continuity of a function. All right, so let's try to work on it. Let me change colors here. This is green marker. I'm kind of curious. Is this any good? Sort of. I'll use it for a little bit. He says, by replacing f with norm f, or f's value of f, we can assume without loss of generality. So basically, without loss of generality, we're going to assume that f is greater than or equal to 0. All right, great. He says, for the first part, let Bn denote the ball of radius n centered at the origin. All right. I've grown tired of this marker as it's invisible to the camera. Let's see here. Whoa, it's got quite an odor too. Let's see here. Bn equal to ball of radius. So it's x in Rd such that the norm of x is less than or equal to n. All right. And he says let or set fn of x to be equal to f of x times chi bn of x. What can we say about this f sub n? I mean, things we can say about this is that fn of x is greater than or equal to 0, for one thing, because we assumed f was positive, non-negative. And he wants to compare fn with fn plus 1. What can you say about fn plus 1 if you think about it? That basically gives you back f of x on a larger sphere, right? So oh, I see. So he says, if you think about this, fn plus 1 of x is greater than or equal to fn of x, right? And the reason for that is they're literally equal all the way out to radius n, right? Past radius n, this one's 0, and this one's just f of x, which is, non-negative. All right, so then what else? What would the limit as n goes to infinity of fn of x give us? Right, just f of x, right? Aha! So by the monotone convergence theorem, what do we get? The limit of the sequence of integrals is the what? The integral of the limit of the sequence, yeah? Because we have met the conditions, the terms and conditions, right, for these help convince us we can apply the monotone convergence theorem on this sequence of measurable functions, which is non-negative, right? But anyway, the point is that this is the integral of f, right? And what does that give us? So he says, okay, so for large enough n, we can do what? We have 0 less than or equal to the integral of f minus the integral of f chi bn less than epsilon. What's f chi bn? What's that? Isn't that just Fn? Yeah, right. Thank you. So, that's what this, so this limiting to that says I can take the difference between the limit and the sequence, right, and make it as small as I like for n sufficiently large. But then this says that 0 is less than, how's he go from here? His next comment is, note that 1 minus chi bn is equal to, this is sneaky, chi bn complement. Does that make sense? That makes a lot of sense, right? If you think about evaluating this function when x is in Bn, you get 1 minus 1, which is 0. When x is in Bn, you get 0, because it's not in Bn complement. If x is not in Bn, though, we get 1 over here, and we get 1 minus 0 over here. So in all possible cases, these functions agree and they're equal. And that's pretty cool because that allows us to take this thing and rewrite it as the integral of f chi bn complement, right? But what is the integral of f chi bn complement? Exactly. That's precisely what we set out to prove in part 1. That's this. So this gives what we want. All right, so then we can try to prove part 2, right? Let's go for it. Do you guys understand why I say that this implies that? Can you break it down for me further, King? I mean, why is it that this so the integral over e of f was defined to be the integral times chi e. Right. And so that, and then also we're assuming that f is equal to the absolute value of f here for this. So it's literally that is, I mean, in short, by the definition, right? Of integral over measurable set. Okay, next up here. He says again, he's just going to give you the proof for f non-negative. And he's going to, again, let fn of x equal to f of x en, well, chi en. But this time, en is a little bit different. En is x such that f of x is less than n, or equal to n. All right. And he points out, so let's see here, fn is greater than or equal to 0, and fn is measurable. All right. What else can we say? How does fn compare to fn plus 1? Is that right? You think it's less than or equal to? I wrote down the wrong inequality, but I'm not sure I understand why. Oh, the en. No, it's less than or equal to. En is less, f of x less than or equal to n. Sorry, I'm having trouble understanding why this is. I'm an idiot. Why is this true? Why is fn of x less than or equal to f n plus 1 of x? I mean, I guess there are two different kinds of x's to consider, right? Like, what if x is, if x is an element of en, then what? So then f of x is less than or equal to n, which is less than n plus 1. So therefore, x is an element of en plus 1, yeah? Which means that fn of x is equal to fn plus 1 of x, right? Because we just multiply by 1 if the condition to be in en is met. So if the condition en implies the condition en plus 1, then that means that chi of en of x is equal to chi of en plus 1 of x. Both of those are 1, and so we get f of x in both cases. So why is the inequality? I mean, I understand the equality case. What do I need? What's the other case to think about? X is what? Not an en, but x is an en plus 1?
No, you just need x not
Say again? Sorry.
You just need x not in en.
Not an en.
Because then you will have fn of x equal to 0.
Uh-huh.
And the other is just not independent,
So then I know that fn of x is 0 and is automatically less than or equal to whatever that is. Yeah, okay. Fair enough. All right. Sorry. I sometimes puzzle over these silly inequalities when they're actually silly. But every so often in this kind of book, when I try to establish the inequality, I found out it's not actually silly, and it's actually something that it's really hard to show. And I'm never quite sure. But these guys are usually pretty honest about what actually takes work and what doesn't, right? So, all right. Let's move along here. So he says, given epsilon greater than 0, there exists, he says by convergence theorem, right? Some n in n sufficiently large such that the integral of f minus fn is less than epsilon over 2. Does that make sense? So the monotonic convergence theorem says that we can do the same thing we did in the proof for part 1, right? Take the limit of fn as n goes to infinity, switch the order of integration and summation, and so yeah. So we can make that less than epsilon over 2, and then he says pick delta greater than 0 such that, ooh, sneaky, n, well, not that sneaky, n delta less than epsilon over 2. All right. What's this E he's talking about? Where's E? What's E? All of a sudden he's talking about E. Am I missing something here? Where's the E? Oh, if the measure of E is less than delta. Excuse, I missed a very important word. If the measure of E is less than delta. So suppose you have a set with measure less than delta, which is the thing we're trying to prove, right? Whenever measure of epsilon is less than delta, we get that the integral over E is less than epsilon. Then we play this game. The integral over E of f, and the old add 0 trick, right? Integral of f minus f n over E plus the integral over E of Fn, so just added 0. But we did so strategically because then, look at this. So rather than just integrating over E, because we don't know anything about, we don't have any bound for E, what we have a bound for is the integral over F, we have a bound for an integral of F minus Fn over all of Rd, namely epsilon over 2 from right here. So he's adding in the rest of the points. Right? So that's epsilon over 2. And what about the Fn piece? He says, he replaces that with n times the measure of epsilon. Where's that coming from? Measure of E. Oh, I think that's just the definition of Fn, right? Fn is the set of points. N is an upper bound. N is an upper bound of, look at what Fn is, right? Fn is only non-zero within En, right? And within En, what serves as an upper bound for F? Or Fn, really. An upper bound for Fn is N within the set on which the integral of F, on which this Fn function is non-zero. So since N is an upper bound, I can replace this with N times the measure of E. But we chose N, what do we have here? Where's the delta? Oh, measure of E is less than delta. Duh. So this is less than epsilon over 2 plus N delta, which, by the way, is less than epsilon, because that's epsilon over 2 plus epsilon over 2. And there you have it. All right. Is good? Is no good?
I'm too tired to do it.
You're too tired to do this? Yeah, I feel that. I know the feeling. I'm actually relatively rested today because I haven't lectured all week. I just lectured on conic sections in abstract, so kind of regressing to college algebra in there. For something different, but I think it's worthwhile. All right. I'm going to write this theorem down. I'm going to decide whether or not we should cover the proof of it, all right? But this is the next one, theorem 1.13. It says, suppose Fn is a sequence of measurable functions such that Fn of x goes to f of x almost everywhere in x as n tends to infinity, period, if the absolute value of Fn of x is less than or equal to g of x, where g is integrable, then the integral of the absolute value of Fn minus f goes to 0 as n goes to infinity. And so the integral of Fn goes to the integral of f as n goes to infinity. He says this is in fact, what I'm writing right now for you is a quote-unquote cornerstone of the theory of Lebesgue integration. It is the so-called dominated convergence theorem. All right. So Emily, we know this is important. We've needed this to understand things that I was talking to you today about in the Fourier analysis, right? So like, I mean, all right. The proof doesn't look too bad. I've said that before. It's less than a page. Maybe we'll understand it. Let's see here. He says, for each n greater than or equal to 0, let En equal to x such that the length of x is less than or equal to n, and g of x is bounded by n, bounded above by n. He says, given epsilon greater than 0, we may argue, as in the first part of the previous lemma, much as we just did, let's say, for the proposition, right? There exists n such that the integral over the complement of En of g is less than epsilon. Whoop. Well, that's not very exciting. Apparently I need to go get diapers. It's an important message to get, though. I'll tell you that right now. You don't want to find yourself without enough of those. It's a bad place to be. Anyway, does that make sense? I think that on the surface of things makes sense that we could do that. So I think the proof of that would be akin to which part? Yeah, part 1 of proposition 112. All right. And then he says the functions f n chi, that's supposed to be a big, come on, that's got to be an uppercase N. There's not many typos in here, though, so that does give me pause. But I feel like that should be f. What do you guys think? It says the functions fn chi en are bounded by n. They're bounded by n and supported on a set of finite measure. Does that make sense? I guess it's clear that the measure of En is finite because it's bounded, it's inside the ball of radius n, right? So it can't have infinite measure.